went on to calculate the orbits of 24 other comets, and to prove that one comet returned to the Sun around every 76 years. Perhaps more importantly, Halley was so impressed by Newton's work that he strongly encouraged him to publish his findings. This resulted in the book Philosophiae Naturalis Principia Mathematica, published in Latin on July 5, 1687, in which Newton describes his laws of motion, his gravitational theory, the proof of Kepler's 3 laws, and the method he used to calculate a comet's orbit. In his book, Newton stressed that his law was universal: gravity affects everything in the universe, regardless of distance. It explained how an apple fell on his head in the orchard of Woolsainthorpe where his mother lived, the tides and the seas, the moon orbiting Earth, Jupiter orbiting the Sun, and even the elliptical orbit of a comet. The physical law that made the apple fall in his yard was exactly the same as the one that shaped the solar system, and would later be discovered at work between stars and distant galaxies. Evidence was all around that Newton's law of gravitation worked. It not only explained where planets had been, but also made it possible to predict where they would go in the future. Constant of proportionality. Newton's law of gravitation states that the size of the gravitational force is proportional to the masses of the two bodies multiplied together and divided by the square of the distance, r, between them. It always draws masses together and acts along a straight line between them. If the object in question is spherically symmetrical, like Earth, then its gravitational pull can be treated as if it were coming from a point at its center. One final value is needed to calculate the force, the constant of proportionality, a number that gives the strength of the force, the gravitational constant. Newton's law of universal gravitation shows how the force produced depends on the mass of the two objects and the square of the distance between them. Measuring g. Gravity is a weak force, and this means that the gravitational constant is rather difficult to measure accurately. The first laboratory test of Newton's theory was made by the English aristocrat scientist Henry Cavendish in 1798, 71 years after Newton's death. He copied an experimental system proposed by the geophysicist John Michell and successfully measured the gravitational force between two lead balls, of diameters 2 and 12 inches. Many have tried to refine and repeat the experiment since. This has led to a slow improvement in the accuracy of g. Some scientists suggested that g changed with time. However, recent analysis of Type 1a supernovae has shown that, over the last 9 billion years, g has changed by less than 1 part in 10 billion, if at all. The light from distant supernovae was emitted 9 billion years ago, allowing scientists to study the laws of physics as they were in the distant past. Nature and nature's laws lay hid in night. God said, "Let Newton be," and all was light. Alexander Pope. Henry Cavendish measured the gravitational constant using a torsion balance. 2 large balls were fixed in place, while 2 smaller balls were attached at either end of a wooden arm suspended from a wire. The gravitational attraction of the small balls to the large ones caused the balance to rotate slightly, twisting the wire. The rotation stopped when the gravitational force equaled the torque of the wire. Knowing the torque for a given angle made it possible to measure the gravitational force. Seeking meaning. Like many of the scientists of his time, Newton was deeply pious and sought a religious meaning behind his observations and laws. The solar system was not regarded as a random collection of planets, and the sizes of the specific orbits were thought to have some specific meaning. For example, Kepler had sought meaning with his notion of the music of the spheres. Building on ideas first put forward by Pythagoras and Ptolemy, Kepler suggested that each planet was responsible for an inaudible musical note that had a frequency proportional to the velocity of the planet along its orbit. The slower a planet moved, the lower the note that it emitted. The difference between the notes produced by adjacent planets turned out to be well-known musical intervals such as major thirds. There is some scientific merit behind Kepler's idea. The solar system is about 4.6 billion years old. During its lifetime, the planets and their satellites have exerted gravitational influences on each other and have fallen into resonant intervals, similar to the way musical notes resonate. Looking at 3 of the moons of Jupiter, for every once that Ganymede orbits the planet, Europa goes around twice and Io 4 times. Over time, they have been gravitationally locked into this resonance. The three-body problem. The solar system as a whole has fallen into similar resonant proportions to Jupiter's moons. On average, each planet has an orbit that is about 73% larger than the planet immediately closer to the Sun. Here, however, there appears a difficult mathematical problem, and one that Newton had grappled with. The movement of a low-mass body under the gravitational influence of a large-mass body can be understood and predicted. But when three bodies are involved, the mathematical problem becomes exceedingly difficult. An example of a three-body system is the Moon-Earth-Sun. Newton thought about this system, but the mathematical difficulties were insurmountable, and human knowledge of where the Moon will be in the distant future is still very limited. Variations in the orbit of Halley's Comet are another indicator of the influence of the gravitational fields of the planets operating in addition to the gravitation of the Sun. Recent orbits have taken 76.0, 76.1, 76.3, 76.9, 77.4, 76.1, 76.5, 77.1, 77.8, and 79.1 years respectively due to the combined gravitational influence of the Sun, Jupiter, Saturn, and other planets on the comet. I have not been able to discover the cause of these properties of gravity from phenomena, and I frame no hypotheses. Isaac Newton. Distant supernovae are seen today as they were billions of years ago. Analysis of their structure shows that the law of gravity operated with the same value of g then as today. Shaping the planets. While Newton searched for religious meaning in his scientific work, he could find none behind his theory of gravity. He did not discover the hand of God setting the planets in motion, but he had found a formula that shaped the universe. The action of gravity is key to understanding why the universe looks as it does. For instance, gravity is responsible for the spherical shapes of the planets. If a body has sufficient mass, the gravitational force that it exerts exceeds the strength of the material of the body and it is pulled into a spherical shape. Astronomical rocky bodies, such as the asteroids between the orbits of Mars and Jupiter, are irregular in shape if they have a diameter of less than about 240 miles. Gravitation is also responsible for the size of the deviations from a sphere that can occur on a planet. There are no mountains on Earth higher than the 5.5 miles of Mount Everest because the gravitational weight of a taller mountain would exceed the strength of the underlying mantle rock and sink. On planets with lower mass, the weight of objects is less, and so mountains can be bigger. The highest mountain on Mars, for instance, Olympus Mons, is nearly 3 times as high as Everest. The mass of Mars is about 1/10 that of Earth, and its diameter is about half Earth's. Putting these numbers into Newton's formula for gravitation, this gives a weight on the surface of Mars of just over 1/3 that on Earth, which explains the size of Olympus Mons. Gravity thus also shapes life on Earth by limiting the size of animals. The largest land animals ever were dinosaurs weighing up to 40 tons. The largest animals of all, whales, are found in the oceans, where the water supports their weight. Gravity is also responsible for the tides, which are produced because water bulges toward the Sun and Moon on the side of Earth nearer to them, and also bulges away from them on the other side where their gravitational pull is weaker. When the Sun and Moon are aligned, there is a high spring tide. When they are at right angles, there is a low neap tide. The motions of the comets are exceedingly regular, and they observe the same laws as the motions of the planets. Isaac Newton. In his great work Principia, Newton plotted the parabolic path of the great comet by taking accurate observations and correcting them to allow for the motion of Earth. Escape velocity. Gravity profoundly affects human mobility. The height a person can jump is determined by the gravitational field at ground level. Newton realized that the strength of gravity would affect the ease of travel beyond the atmosphere. To break free from Earth's gravitational pull, it is necessary to travel at 25,020 miles per hour. It is much easier to get away from less massive bodies such as the Moon and Mars. Turning the problem around, this escape velocity is also the minimum velocity that an incoming asteroid or comet can have when it hits Earth's surface, and this affects the size of the resulting crater. Today, gravity is held to be most accurately described by the general theory of relativity proposed by Albert Einstein in 1915. This does not describe gravity as a force, but instead as a consequence of the curvature of the continuum of spacetime due to the uneven distribution of mass inside it. This said, Newton's concept of a gravitational force is an excellent approximation in the vast majority of cases. General relativity only needs to be invoked in cases requiring extreme precision or where the gravitational field is very strong, such as close to the Sun or in the vicinity of a massive black hole. Massive bodies that are accelerating can produce waves in spacetime, and these propagate out at the speed of light. The first detection of one of these gravitational waves was announced in February 2016. Newton illustrated escape velocity with a thought experiment of a cannon firing horizontally from a high mountain. At velocities less than orbital velocity at that altitude, the cannonball will fall to Earth. At exactly orbital velocity, it will enter a circular orbit. At greater than orbital velocity but less than escape velocity, it will enter an elliptical orbit. Only at escape velocity will it fly off into space. Isaac Newton. Isaac Newton was born on a farm in Woolsainthorpe, Lincolnshire, on December 25, 1642. After school in Grantham, he attended Trinity College, Cambridge, where he became a fellow and taught physics and astronomy. His book Principia set out the principle of gravity and celestial mechanics. Newton invented the reflecting telescope, wrote theses on optics, the prism, and the spectrum of white light, was one of the founders of calculus, and studied the cooling of bodies. He also explained why Earth was oblate in shape and why the equinox moved, and formalized the physics of the speed of sound. He spent much time on biblical chronology and alchemy. Newton was at various times President of the Royal Society, Warden and Master of the Royal Mint, and Member of Parliament for Cambridge University. He died in 1727. Key works: 1671 Method of Flux Ions, 1687 Philosophiae Naturalis Principia Mathematica, 1704 Optics. See also: Elliptical orbits, Halley's Comet, the discovery of Neptune, the theory of relativity, Lagrange. In context: Key astronomer Edmund Halley. Before c. 350 BCE Aristotle declares that comets are weather phenomena in Earth's upper atmosphere. 1577 Tycho Brahe calculates that a comet he has observed must exist far outside Earth's atmosphere. After 1758 the comet that Halley predicted duly reappears, 76 years after its last sighting. 1819 German astronomer Johann Encke discovers a second periodic comet, which reappears every 3.3 years. 1950 Dutch astronomer Jan Oort proposes that the solar system is surrounded by a huge cloud of comets, and that stars may perturb their orbits. In the 16th century and for much of the 17th, advances were made in understanding the motions of planets, but the nature of comets remained a mystery. Up until at least 1500, comets had been feared as harbingers of doom in Europe. Astronomers were familiar with these bright blotches of light and their long, beautiful tails moving slowly across the sky over periods of a few weeks or months, but had no idea where they came from, nor where they disappeared to. Things changed, however, in 1577, when an exceptionally bright comet lit up the night sky for several months. By studying observational data from different parts of Europe, the Danish astronomer Tycho Brahe calculated that the comet must be at least 4 times farther away than the Moon, and this allowed him to fit comets into his model of the universe. He saw them as objects that could move freely through the same regions of space as planets. But what was not agreed on in Brahe's time, nor for many decades afterward, was the shape of the paths that comets carved through space. Brahe's one-time student Johannes Kepler believed that they traveled in straight lines. Polish astronomer Johannes Hevelius, however, suggested that a comet of 1664 had traveled in a curved orbit around the Sun. Halley's Comet appeared in 1066 and is shown in the Bayeux Tapestry, with Anglo-Saxons pointing fearfully at the sky. Its appearance was taken by some to foretell the fall of England. Newton tackles comets. From about 1680, stimulated by the appearance of a particularly bright comet that year, the great English scientist Isaac Newton began studying cometary orbits while developing his universal theory of gravitation. Using his new theory, Newton analyzed and predicted the future path that the 1680 comet would take. He came to the conclusion that comets had orbits in the shapes of ellipses, with the Sun at one focus of the ellipse. These ellipses were so stretched out, however, that they could be approximated to an open-ended curve called a parabola. If Newton was right, then once a comet had visited the inner solar system and curved around the Sun, it would either never return or would not return for thousands of years. In 1684, Newton received a visit from a young acquaintance named Edmund Halley, who was interested in discussing what force might account for the motions of planets and other celestial bodies such as comets. Newton told his astonished visitor that he had been studying the matter himself and had already solved the problem, but that he had not yet published his findings. This meeting eventually led to Halley editing and financing the publication in 1687 of Newton's great book on gravity and the laws of motion, Philosophiae Naturalis Principia Mathematica. Historical records. Halley suggested to Newton that he might apply his new theory to studying the orbits of more comets. However, Newton's mind had turned to other matters, so, from the early 1690s, Halley conducted his own detailed study. In all, over a period of more than 10 years, he studied the orbits of 24 comets, some that he had observed himself and others for which he had obtained data from historical records. He suspected that, while some comets followed paths that are parabolas as Newton had proposed, others followed elliptical orbits, meaning that they might pass through the inner solar system and thus become visible from Earth, more than once in a person's lifetime. During his studies, Halley had noticed something strange. In general, the orbit of each comet had a few characteristics that clearly distinguished it from the orbits of other comets, such as its orientation in relation to the stars. However, 3 of the comets he had studied, one he had seen himself in 1682, and others observed by Kepler in 1607, and Petrus Apianus in 1531, seemed to have remarkably similar orbits. He suspected that these were successive reappearances, which occurred about once every 75 to 76 years, of the same comet, which was traveling on a closed, elliptical orbit. In 1705, Halley outlined his ideas in a paper called Astronomiae Cometicae Synopsis. He wrote, "Many considerations incline me to believe the comet of 1531 observed by Apianus to have been the same as that described by Kepler and Longomontanus in 1607 and which I again observed when it returned in 1682. All the elements agree. Whence I would venture confidently to predict its return, namely in the year 1758. One uncertainty still worried Halley. The time intervals between the 3 appearances were not precisely the same, they differed by about a year. Remembering research he had done some years earlier on Jupiter and Saturn, Halley suspected that the gravitational pull from these 2 giant planets might slightly throw the comet off its course and delay its timing. Halley asked Newton to reflect on this problem, and Newton came up with gravitational calculations by which Halley was able to refine his forecast. His revised prediction was that the comet would reappear either in late 1758 or in early 1759. Even in an age renowned for unusual savants, Halley stands out as a man of extraordinary breadth and depth. J. Donald Fernie, Professor Emeritus of Astronomy at the University of Toronto. Some comets follow a parabolic or hyperbolic path, meaning that they will never return. Others follow elliptical curves of varying extent. Halley suggested that if a comet followed a moderately stretched elliptical curve, it could return every 50 to 100 years. Halley is proved right. Interest in Halley's prediction spread throughout Europe. As the year of the comet's predicted return approached, 3 French mathematicians, Alexis Clairaut, Joseph Lalande, and Nicole Reine-Lepaute, spent several arduous months recalculating when it might reappear, and where it might first be seen in the night sky. Amateur and professional astronomers alike began watching for the comet's return as early as 1757. On December 25, 1758, it was finally spotted by Johann Palitzsch, a farmer and amateur astronomer from Germany. The comet passed closest to the Sun in March 1759, only a couple of months later than Halley had predicted. By then, Halley had been dead for 17 years, but the comet's reappearance brought him posthumous fame. The comet was named Halley's Comet in his honor by the French astronomer Nicolas Louis de Lacaille. Halley's Comet was the first object other than a planet that had been proven to orbit the Sun. It also provided one of the earliest proofs of Newton's theory of gravity, demonstrating that the theory could be applied to all celestial bodies. Comets themselves, once feared as unpredictable omens of ill fortune, were now understood. Subsequent research found that the comet had made regular appearances going back to at least 240 BCE, including some particularly bright apparitions in 87 BCE, 12 BCE, 837 CE, 1066, 1301, and 1456. In 1986, the comet was closely approached by spacecraft, which provided data on the structure of its nucleus and its tail. It is the only known short-period comet that may be seen with a naked eye and appear twice in a human lifetime. On its last appearance in 1986, Halley's Comet passed to within 0.42 astronomical units of Earth. It has passed much closer. In 1066, for instance, it came within 0.1 Australian dollars. Aristotle's opinion that comets were nothing else than sublunary vapors prevailed so far that this sublimest part of astronomy lay altogether neglected. Edmund Halley. Edmund Halley. Edmund Halley was born in 1656 in London. In 1676, he sailed to the island of St. Helena in the South Atlantic, where he charted the stars of the Southern Hemisphere, publishing a catalogue and star charts after his return. In 1687, he helped persuade Isaac Newton to publish Principia, which included details on how to calculate cometary orbits. Halley was appointed Astronomer Royal in 1720, and he resided at the Royal Observatory, Greenwich, until his death in 1742. Although remembered mainly as an astronomer, Halley did important work in many fields. He published studies on variations in Earth's magnetic field, invented and tested a diving bell, devised methods for calculating life insurance premiums, and produced oceanic charts of unprecedented accuracy. Key works: 1679 Catalogus Stellarum Australium, 1705 Astronomiae Cometicae Synopsis. 1716 An account of several nebulae. See also, the Tychonic model, elliptical orbits, gravitational theory. In context. Key astronomer James Bradley. Before 17th century, the general acceptance of a sun-centered cosmos leads astronomers to search for stellar parallax, the apparent movement of stars caused by Earth's movement. 1676 Danish astronomer Ole Romer estimates the speed of light using observations of the Jovian satellites. 1748 Swiss mathematician Leonhard Euler outlines the physical cause of nutation. After 1820 German optician Joseph von Fraunhofer builds a new type of heliometer for the study of stellar parallax. 1838 Friedrich Bessel measures the parallax of the star 61 Cygni. He finds that it is 600,000 times farther away from Earth than the Sun. In the 1720s, while seeking proof that Earth was moving by tracking changes in the apparent positions of stars, Oxford astronomer James Bradley found another phenomenon that also provided proof: stellar aberration. The aberration of light causes objects to appear to be angled toward the direction of a moving observer. Aberration angles are tiny, no more than the speed of Earth perpendicular to the star's direction divided by the speed of light, which is 20 arcseconds at most. Earth moves at about 20 miles s, but both its speed and direction of travel change as it orbits the Sun. As a result, a star's observed position follows a small ellipse around its real position. Bradley observed this in the case of the star Gamma Draconis, the first irrefutable proof that Earth moves. He also discovered another periodic variation in star positions, called nutation. Like aberration, the effect is small. Earth's spin axis gradually changes its orientation in space. The greatest change is precession, and a full cycle takes 26,000 years to complete. Nutation is a small wobble in precession with an 18.6-year cycle. Precession and nutation are both caused by gravitational interactions between the Moon, Earth, and Sun. Bradley made his discovery public in 1748, after 20 years of observations. Stellar aberration is caused by Earth's movement. Changes in Earth's velocity can be detected through changes in the position of the stars. See also, shifting stars stellar parallax Romer. In context. Key astronomer. Nicolas Louis de Lacaille. Before 150 CE, Ptolemy lists the 48 constellations that can be seen from Mediterranean latitudes. 1597, Petrus Plancius, a founder of the Dutch East India Company, uses the findings of explorers Kaiser and de Houtman to introduce 12 new southern constellations on his celestial globes. C. 1690, Prodomus Astronomiae, by Polish astronomer Johannes Hevelius, names 7 new constellations still in use. After 1801, Johann Bode's Uranographia, a collection of 20 star maps, is the first near-complete guide to stars that are visible to the naked eye. 1910, schoolmaster Arthur Norton produces his star atlas, which is popular for a century. French astronomer and mathematician Nicolas Louis de Lacaille had the idea to use trigonometry to measure the distance to the planets after observing them from different places. To provide the longest possible baseline for his calculations, Lacaille needed simultaneous observations in Paris and at the Cape of Good Hope. To this end, he traveled to South Africa in 1750 and set up an observatory at Cape Town. There, he not only observed the planets, but also measured the positions of 10,000 southern stars. His results were published posthumously in 1763 in Colum Australe Stelliferum. They proved to be his greatest legacy to astronomy. Southern stars. Parts of the sky surveyed by Lacaille are too far south to be visible from Europe, and many of the stars he observed had not been allocated to constellations. To give designations to the stars in his catalogue, Lacaille introduced 14 new constellations that are still recognized and used today, and he defined the boundaries of existing southern constellations. Before leaving South Africa, he also carried out a major surveying project with the aim of better understanding the shape of the Earth. Lacaille was a zealous and highly skilled observer who appreciated the value of accurate measurements. He demonstrated an exceptional ability and energy to pioneer a thorough survey of the southernmost sky. Lacaille laid the foundation of exact sidereal astronomy in the southern hemisphere. Sir David Gill. See also, Consolidating Knowledge, the Southern Hemisphere. Introduction. In the space of 75 years across the 18th and 19th centuries, 2 new planets were discovered, bringing the number of known major planets to 8. However, the circumstances under which Neptune was found in 1846 were very different from those that resulted in the accidental identification of Uranus in 1781. In between these 2 discoveries, many other bodies were found in the solar system, showing that it contains a far greater number and variety of objects than had previously been imagined. Powers of observation. Briton William Herschel is considered by many to have been the greatest visual astronomer of all time. He built better telescopes than any of his contemporaries and was an obsessive observer of apparently boundless stamina and enthusiasm. In addition, he persuaded members of his family to help his enterprises, notably his sister Caroline, who gained recognition as an astronomer in her own right. William was not looking for a planet when he noticed Uranus, but his discovery was a consequence of his skill at telescope making and systematic approach to observing, which enabled him to spot the movement of the planet over time. Herschel also studied double and multiple stars, catalogued nebulae and star clusters, and attempted to map the structure of the Milky Way. Always alert to the unexpected, he discovered infrared radiation by accident when studying the spectrum of the Sun in 1800. Better telescopes led to far more detailed surveys of the sky. William's son, John Herschel, inherited his father's aptitude for astronomy and spent 5 years in South Africa completing his father's surveys. William Parsons, 3rd Earl of Rosse, took the next big step in the investigation of nebulae. In the 1840s, he set himself the ambitious task of constructing the largest telescope in the world. With it, he discovered that some nebulae have a spiral structure. All the effects of nature are only the mathematical consequences of a small number of immutable laws. Pierre-Simon Laplace. More planets. Herschel's discovery of Uranus aroused fresh interest in the wide gap in the solar system between the orbits of Mars and Jupiter. The regular spacing of the other planets suggested that there was an unknown planet in the gap. It turned out to be occupied not by a single major planet but by numerous minor planets, which William Herschel dubbed asteroids. Italian Giuseppe Piazzi discovered the first asteroid, Ceres, in 1801, as he was observing for a new star catalogue. 3 more were located in the following 6 years. The next was not found until 1845, after which the pace of discovery increased. Meanwhile, German Ernst Chladni had correctly concluded that meteorites reaching Earth are chunks of rock and metal from space. Clearly, the solar system contained a great variety of bodies. The might of mathematics. By contrast to the fortuitous discovery of Uranus, the discovery of Neptune was a demonstration of the power of mathematics. While astronomers were working with better telescopes, mathematicians grappled with the practical difficulties of applying Newton's theory of gravitation to the complex interplay of gravitational forces between the larger bodies of the solar system. The calculations of German mathematician Carl Friedrich Gauss in 1801 allowed Ceres to be relocated, while between 1799 and 1825, Frenchman Pierre-Simon Laplace produced a monumental definitive work on celestial mechanics. It soon became evident that Uranus was not following its predicted course. The pull of an unknown planet was suspected. Building on Laplace's work, compatriot Urbain Le Verrier tackled the problem of predicting the undiscovered planet's possible position. Neptune was duly found close to where Le Verrier thought it would be. For the first time, astronomers now had an idea of the true extent of the solar system. In context. Key astronomer. William Herschel. Before 1660s mirror-based reflecting telescopes are developed by Isaac Newton and others. 1690 John Flamsteed observes Uranus, but believes it to be a star. 1774 French astronomer Charles Messier publishes his astronomical survey, which inspires Herschel to begin work on a survey of his own. After 1846 unexplained changes to the orbit of Uranus lead French mathematician Urbain Le Verrier to predict the existence and position of an 8th planet, Neptune. 1930 U.S. astronomer Clyde Tombaugh discovers Pluto, a 9th planet. It has since been reclassified as a dwarf planet, the brightest member of the Kuiper belt of small, icy worlds. Uranus, the 7th planet from the Sun, is visible to the naked eye, and it is believed that the ancient Greek Hipparchus observed it in 128 BCE. The development of telescopes in the 17th century led to further sightings, such as one by English astronomer John Flamsteed in 1690 when it was recorded as 34 Tauri, a star. It was also observed by the French astronomer Pierre Lemonnier several times between 1750 and 1769. However, none of the observers figured out that it was a planet. William Herschel observed Uranus on March 13, 1781, while looking for multiple star systems. He spotted it again 4 nights later, and on this second occasion he noticed that its position had changed in relation to the stars around it. He also noted that if he increased the power of the telescope he was using, the new object increased in size more than the fixed stars. These 2 observations indicated that it was not a star, and when he presented his discovery to the Royal Society he announced that he had found a new comet. The Astronomer Royal, Neville Maskelyne, looked at Herschel's discovery and decided that the new object was as likely to be a planet as a comet. Swedish-Russian Anders Johann Lexell and German Johann Alert Bode independently computed the orbit of Herschel's object and concluded that this was a planet in a near-circular orbit, roughly twice as far away as Saturn. I compared it to H. Geminorum and the small star in the quartile between Auriga and Gemini, finding it so much larger than either of them. William Herschel. Naming the planet. Herschel's discovery was praised by King George III, who appointed Herschel the king's astronomer. Maskelyne asked Herschel to name the new planet, and he chose Georgium Sidus in honor of his patron. Other names, including Neptune, were proposed, and Bode suggested Uranus. His suggestion became universal in 1850, when the UK's Greenwich Observatory finally abandoned the name Georgium Sidus. The detailed study of the orbit of Uranus by subsequent astronomers showed that there were discrepancies between its observed orbit and the orbit predicted according to Newton's laws, irregularities that could only be explained by the gravitational influence of an eighth, even more distant planet. This led to the discovery of Neptune by Urbain Le Verrier in 1846. Herschel observed Uranus using a 7-foot reflector telescope. He would later construct a 40-foot telescope, which was the largest telescope in the world for half a century. William Herschel. Born in Hanover, Germany, Frederick William Herschel emigrated to Britain at the age of 19 to make a career in music. His studies of harmonics and mathematics led to an interest in optics and astronomy, and he set out to make his own telescopes. Following his discovery of Uranus, Herschel detected 2 new moons of Saturn and the largest 2 moons of Uranus. He also showed that the solar system is in motion relative to the rest of the galaxy and identified numerous nebulae. While studying the Sun in 1800, Herschel discovered a new form of radiation, now known as infrared radiation. Herschel's sister Caroline acted as his assistant, polishing mirrors and recording and organizing his observations. She began to make observations of her own in 1782, and went on to discover a number of comets. Key works: 1781 Account of a Comet. 1786 Catalogue of 1,000 new nebulae and clusters of stars. See also, Shifting Stars Gravitational Theory, the discovery of Neptune. In context. Key astronomer John Goodricke. Before 130 BCE, Hipparchus defines a magnitude scale for the apparent brightness of stars, which is popularized by Ptolemy in the Almagest. 1596 David Fabricius discovers that the star Mira Ceti varies in brightness with periodic regularity. After 1912 Henrietta Swan Leavitt discovers that the period of some variable stars is related to their absolute brightness. 1913 Ejner Hertzsprung calibrates this variation in brightness, allowing Cepheid variables to be used as standard candles to calculate the distance to galaxies. 1929 Edwin Hubble identifies the link between the velocity of a galaxy and its distance. Ancient Greek astronomers were the first to classify stars by their apparent brightness, that is, their brightness as observed from Earth. In the 18th century, British amateur astronomer John Goodricke grew interested in changes in apparent brightness after his neighbor, astronomer Edward Pigott, provided him with a list of stars known to vary. In the course of his observations, he discovered more. In 1782, Goodricke observed the variation in brightness of Algol, a bright star in the constellation Perseus. He was the first person to propose a reason for this change in brightness, suggesting that Algol was in fact a pair of stars orbiting one another, with one brighter than the other. When the dimmer of the two stars passed in front of the brighter one, the eclipse would reduce the brightness detected by observers. Today this is referred to as an eclipsing binary system. Goodricke also discovered that the star Delta Cephei in the constellation Cepheus varies in brightness with a regular period. It is now known that Delta Cephei is one of a class of stars whose apparent brightness varies because the star itself changes. Stars such as this are called Cepheid variables, and they are key to calculating the distance to other galaxies. Goodricke presented his findings to the Royal Society in 1783. He died shortly after from pneumonia, at just 21 years old. In an eclipsing binary system, maximum brightness occurs when both stars are visible, minimum brightness occurs when the dim star is eclipsing the bright star. See also, a new kind of star measuring the universe beyond the Milky Way. In context. Key astronomer Charles Messier. Before 150 CE Ptolemy records 5 stars that appear nebulous and 1 nebula not linked to a star. 964 Persian astronomer Abd al-Rahman al-Sufi notes several nebulae in his Book of Fixed Stars. 1714 Edmund Halley publishes a list of 6 nebulae. 1715 Nicolas Louis de Lacaille identifies 42 nebulae. After 1845 Lord Rosse observes that some nebulae have a spiral structure. 1864 William Huggins examines the spectra of 70 nebulae, finding that a third of them are clouds of gas, while the rest are masses of stars. 1917 Vesto Slipher identifies spiral nebulae as distant galaxies. By the 18th century, large telescopes that could magnify images by several hundred times were being produced. This allowed astronomers to identify various fuzzy patches of light, which were called nebulae, after the Latin word for cloud. French astronomer Charles Messier was primarily interested in finding comets, which often looked just like nebulae. A fuzzy object could only be identified as a comet if it changed position against the stars over a period of weeks or months. Messier therefore compiled a list of known nebulae to eliminate them as potential comets. His initial list was published in 1774 and identified 45 nebulae. The final 1784 version listed 80 objects. These nebulae are now known as Messier objects. Other astronomers added further nebulae that were observed by Messier but not recorded by him in his catalogue, bringing the total to 110. With more powerful telescopes, it has been possible to determine the nature of the Messier objects. Some are galaxies beyond the Milky Way, some are clouds of gas where stars are forming, and others are the remains of supernova explosions or the gas thrown off by dying stars the size of our Sun. Messier 31 is also known as the Andromeda Galaxy. It is the nearest major galaxy to the Milky Way. See also, Halley's Comet mapping southern stars examining nebulae properties of nebulae spiral galaxies. In context. Key astronomer. William Herschel before. 1725 English astronomer John Flamsteed's catalogue of 3,000 stars is issued, followed by his star atlas in 1729. 1750 Thomas Wright suggests that the solar system is part of a disk of stars. 1784 Charles Messier produces his final catalogue of nebulae. After 1833 John Herschel continues his father's work, publishing a systematic mapping of the sky including observations made from the southern hemisphere. 1845 Lord Rosse observes that some nebulae have a spiral structure. 1864 William Huggins uses emission spectra to determine that some nebulae are masses of stars. One of the most spectacular features in the sky visible to the naked eye is the dense band of light called the Milky Way. This light from billions of stars is not seen by many people today because of light pollution, but was a common sight before street lighting. In the 1780s, British astronomer William Herschel attempted to determine the shape of the Milky Way and the Sun's position within it by observing the stars. In this endeavor, Herschel built upon the work of his compatriot Thomas Wright, who, in 1750, had argued that the stars appeared as a band of light because they were not randomly scattered but formed a vast ring around Earth, held together by gravity. The Milky Way appeared to circle Earth, and so Herschel concluded that the galaxy was disk-like. He observed the numbers of stars of different magnitudes and discovered that these were equally distributed within the band of the Milky Way in all directions. This led him to assume that the brightness of a star indicated its distance from Earth, with dimmer stars being more distant. The even distribution, he believed, must mean that the solar system was close to the center of the galaxy. Herschel's model was refined by other astronomers, but was not replaced until the early 20th century. From Earth, the Milky Way appears as a band of light whose individual stars cannot be seen with the naked eye. The band is the galaxy's disk-shaped structure viewed from within. New nebulae. Herschel did not limit himself to the study of stars in his investigation into a galaxy's shape. He also observed nebulae, the fuzzy patches of light that dotted the sky. Herschel was a skilled telescope maker as well as an astronomer, and used two large, powerful telescopes with 49 1/2 in and 18 1/2 in apertures. From 1782, he used these instruments to conduct systematic observations of the deep sky, searching for objects that were not stars. He listed these as nebulae or as clusters of stars, and published details of 1,000 new objects in 1786, with further catalogues appearing in 1789 and 1802. Herschel classified the objects he listed into 8 categories, depending on their brightness, size, or whether they appeared to consist of dense or scattered clusters of stars. He also conjectured that most nebulae were similar in nature and size to the Milky Way, decades before it was confirmed that nebulae were in fact galaxies in their own right. The current model of the Milky Way is a barred spiral galaxy. Around 2/3 of spiral galaxies have central bars like the Milky Way's. The early idea of a disk of stars is broadly correct, But the stars within the disk are arranged in a series of spiral arms, with the Sun in a sparse area of the Orion, Cygnus arm. The Milky Way comprises stellar arms spiraling out from the bulging bar at the center. The arms are labeled here. The Sun is located in the Orion, Cygnus arm, 26,000 light-years from the center. I have observed stars of which the light, it can be proved, must take 2 million years to reach the Earth. William Herschel. See also, Messier objects the southern hemisphere properties of nebulae spiral galaxies the shape of the Milky Way. In context. Key astronomer Ernst Chladni. Before 1718 Isaac Newton proposes that nothing can exist between the planets. 1771 A spectacular fireball is recorded passing over Sussex in southern England and continuing to be seen over northern France. After 1798 British chemist Edward Howard and French mineralogist Jacques-Louis de Bournon analyze stones and irons from falls in Italy, England, and India. They find similar proportions of nickel in the stones, indicating a link between them. 1801 Giuseppe Piazzi discovers Ceres, the largest object in the asteroid belt, now classed as a dwarf planet. In the 18th century, the real source and nature of what are now called meteorites was not known. Interplanetary space was thought to be empty, and the fiery lumps of rock and iron that fell from the sky were believed to originate either in volcanoes on Earth that had thrown them up, or from dust in the atmosphere, perhaps by the action of lightning. This idea can be traced back to Isaac Newton, who wrote that it was necessary to empty the heavens of all matter in order for the planets and comets to move unimpeded in their regular orbits. In the early 1790s, a German physicist named Ernst Chladni attempted to solve the mystery of these fallen stones by examining historical records. One that he studied had landed in 1768 in France, where it had been subjected to chemical analysis. The results showed that it had formed from a lump of sandstone that had been struck by lightning and flung into the air. Chladni then examined an object found in 1772 that had a mass of more than 1,500 pounds. It had a rough surface, was filled with cavities, and was totally unlike the rock of the landscape where it was found. It had also very clearly been melted. This iron-nickel meteorite was found on an Arctic ice sheet. The odd shape of the meteorite is due to spinning and tumbling at a high temperature on entry into the atmosphere. Falling from space. Chladni realized that neither lightning nor a forest fire could have produced enough heat to melt bedrock. Yet the rock he examined had become a mass of metallic iron. This iron, he concluded, could only have come from space. It had melted on its passage through the atmosphere. Chladni published his findings in a book in 1794, which set out his main conclusions, that masses of iron or stone fall from the sky, and that friction in the atmosphere causes them to heat up, creating visible fireballs. That the masses do not originate in Earth's atmosphere but far beyond it. And that they are fragments of bodies that never join together to make planets. Chladni's conclusions were correct, but at the time he was ridiculed, until some chance rockfalls helped to change opinion. The first of these took place within 2 months of the publication of Chladni's book, when a large fall of stones came down on the outskirts of Siena, Italy. Analysis of them showed they were very different from anything found on Earth. Then, in 1803, nearly 3,000 stones fell in fields around L'Aigle in Normandy. French physicist Jean-Baptiste Biot investigated this fall. He concluded that they could not have originated anywhere nearby. Solar system fragments. Thanks to Chladni's work, scientists know that shooting stars are lumps of rock or metal from space heated to glowing point as they pass through the atmosphere. The object that causes the glowing trail is called a meteor. If any of it survives to reach the ground, it is termed a meteorite. Meteorites can originate in the asteroid belt between Jupiter and Mars, or they can be rocks thrown up from Mars or the Moon. Many meteorites contain small particles called chondrules, which are thought to be material from the asteroid belt that never formed into larger bodies. These are some of the oldest materials in the solar system, and can tell scientists much about its early composition. Ernst Chladni. Ernst Chladni was born in Saxony to a family of prominent academics. Chladni's father disapproved of his son's interest in science and insisted he study law and philosophy. He obtained a degree in these subjects from the University of Leipzig in 1782. However, when his father died that year, he turned to physics. Initially, Chladni applied his physics knowledge to work in acoustics, which brought him renown. He identified the way rigid surfaces vibrate, and his observations were applied to the design of violins. His later work on meteorites drew less favorable attention from the scientists of the day, and might have vanished into obscurity had it not been for the popular writing of Jean-Baptiste Biot, whose findings supported Chladni's ideas. Key works: 1794 on the origin of the iron masses found by Pallas and others similar to it, and on some associated natural phenomena. 1819 igneous meteors and the substances that have fallen from them. See also, gravitational theory, the discovery of series investigating craters. In context. Key astronomer: Pierre-Simon Laplace. Before 1609 Johannes Kepler determines that the planets move in elliptical orbits. 1687 Isaac Newton publishes Principia Mathematica, which includes his law of universal gravitation and a mathematical derivation of Kepler's laws of planetary motion. 1734 Swedish philosopher Emanuel Swedenborg outlines the nebular theory of the formation of the solar system. After 1831 Mary Somerville translates Laplace's Mécanique Céleste to English. 1889 French mathematician Henri Poincaré shows that it is not possible to prove that the solar system is stable, laying the foundations for chaos theory. By the end of the 18th century, the structure of the solar system was well known. The planets moved in elliptical orbits around the Sun, held in place by gravity. Isaac Newton's laws allowed a mathematical basis for this model of the solar system to be developed, but there were still problems. Newton himself tested his ideas against observations, but noted perturbations to the planet's orbits. By this he meant a disturbance to the orbits caused by an additional force, which would make the orbits unstable if not corrected. As a result, Newton decided that the hand of God was occasionally required to maintain the solar system in a stable state. Orbital resonance. French mathematician Pierre-Simon Laplace rejected the notion of divine intervention, however. In 1784, he turned his attention to a long-standing question known as the Great Jupiter-Saturn inequality. Laplace showed that perturbations in the orbits of these two planets were due to the orbital resonance of their motions. This refers to the situation in which the orbits of two bodies relate to each other in a ratio of whole numbers. In the case of Jupiter and Saturn, Jupiter orbits the Sun almost exactly 5 times for every 2 orbits of Saturn. This means that their gravitational fields have a greater effect on each other than they would for orbits that are not in resonance. Orbital resonance occurs when the gravity of orbiting bodies produces a stable and self-correcting system. An example is the orbits of the neighboring giant planets Jupiter and Saturn, whose orbital periods are in a ratio of 5:2. The nebular hypothesis. Laplace published his work on the solar system in 2 influential books, a popular account called Exposition du Système du Monde and the Mathematical Mécanique Céleste. In his exposition, Laplace explored the idea that the solar system developed from a primeval nebula. Laplace described a rotating mass of hot gases that cooled and contracted, breaking off rings from its outer edge. The core material formed the Sun and the matter in the rings cooled to form the planets. Shortly after Laplace's death, his work was translated into English by the Scottish mathematician Mary Somerville, and this led to a wide dissemination of his ideas. Using Laplace's new theorems, his fellow countryman Jean-Baptiste Joseph D'Alembert was able to produce far more accurate tables predicting the motions of Jupiter and Saturn. Pierre-Simon Laplace. Pierre-Simon Laplace was born in Normandy, France, to a minor landowner. His father intended him for the church, and he studied theology at the University of Caen, but it was there that he developed his interest in mathematics. He gave up any intention of entering the priesthood and moved to Paris, where he obtained a teaching position in the École Militaire. Here, he taught a young Napoleon Bonaparte. The post allowed him time to devote himself to research, and through the 1780s, he produced a string of influential mathematical papers. When Napoleon seized power in 1799, Laplace became a member of the Senate and served on many scientific commissions. He continued to work on the mathematics of astronomy until his death, publishing 5 volumes on celestial mechanics. Key works: 1784 Théorie du mouvement et de la figure elliptique des planètes, 1786 Exposition du système du monde, 1799, 1825 Mécanique céleste. See also, Elliptical orbits, Galileo's telescope, Gravitational theory, The theory of relativity, D'Alembert. In context. Key astronomer Giuseppe Piazzi. Before 1596 Johannes Kepler suggests there are unobserved planets in the solar system. 1766 Johann Titius predicts the gap between Mars and Jupiter contains a planet. 1781 William Herschel's discovery of Uranus confirms the pattern of orbits proposed by Johann Bode. 1794 Ernst Chladni suggests meteorites are rocks that were once in orbit. After 1906 Trojan asteroids are found in the orbit of Jupiter. 1920 Hidalgo, the first Centaur asteroid, is found between Jupiter and Neptune. 2006 Ceres is classified as a dwarf planet. For centuries, the number of known wandering stars, or planets, that trailed through the night sky was 5. Together with the Sun and Moon, that brought the total of major celestial bodies visible from Earth to 7, a number imbued with mystical significance. Then, in 1781, William Herschel spotted Uranus out beyond the orbit of Saturn, which forced astronomers to rethink this number. However, when the new planet's orbit was placed in an updated plan of the solar system, it revealed another number conundrum. Finding a gap. In 1766, a German astronomer named Johann Titius discovered a mathematical link between the orbital distances of the planets. He divided the orbital distance of Saturn by 100 to create a unit to measure all the other orbits. Mercury's orbit was 4 units from the Sun, and every other planet's position from there was linked to a doubling of 3, or the number sequence 0, 3, 6, 12, 24, 48, and 96. So Mercury was located at 4 plus 0 units from the Sun, Venus at 4 plus 3, Earth at 4 plus 6, and Mars was at 4 plus 12. Jupiter was at 4 plus 48 and Saturn was at 4 plus 96. There was no known planet in the sequence at 4 plus 24 is equal to 28, so there appeared to be a gap in the solar system between Mars and Jupiter. Titius proposed that the gap must be occupied by an unknown body. However, his findings seemed too good to be true, and the results for Mars and Saturn were slightly out, so few astronomers paid them much heed. A few years later, in 1772, a fellow German named Johann Bode published a slightly modified version of Titius's work, which met with greater acclaim. As a result, the theory is best remembered as Bode's law. When Uranus was discovered, Bode's law predicted that it would be 196 units from the Sun. It was finally shown to be nearer to 192 units, but that seemed close enough. Surely, it meant the 28-unit gap must also contain a planet. In 1800, a group of German-based astronomers led by Franz Xaver von Zach, Heinrich Olbers, and Johann Schroeder decided to launch a search of the gap. Their plan was to divide up the zodiac, the strip of sky in which all the planets move, and ask Europe's top 24 astronomers to patrol one zone each, searching for planet-like motion. The team they put together was dubbed the Celestial Police. But in the end it was straightforward luck, not efficiency, that filled the gap. From Mars there follows a space of 4 plus 24 is equal to 28 such parts, but so far no planet was sighted there. But should the Lord Architect have left that space empty? Not at all. Johann Titius. Photographed by NASA's Dawn spacecraft in 2015, Ceres is the largest object in the asteroid belt, and the only object large enough to have been made spherical by its own gravity. Surveying telescope. One of the astronomers among the Celestial Police was Giuseppe Piazzi, who was based in Palermo, Sicily. Like most astronomers at the time, Piazzi was mainly concerned with creating accurate star maps. To that end, he had acquired a surveying telescope now known as the Palermo Circle. Although it was not the most powerful telescope of its day, its altazimuth mounting could move both vertically and horizontally, enabling it to make very accurate measurements of stellar positions, a feature that would pay rich dividends. On the evening of New Year's Day 1801, the instructions from the Celestial Police were still en route to Piazzi, so he spent the evening surveying stars and recorded a new, faint object in the constellation of Taurus. The following night, Piazzi checked his measurements and found that the object had moved slightly. This meant it was definitely not a star. Piazzi watched the object for 24 days before informing Bode. He thought at first that it was a comet, a relatively common discovery, but his observations soon suggested otherwise. He could see no fuzzy coma or tail, and while comets sped up as they approached the Sun, Piazzi's discovery took a more stable, circular path. In his letter to Bode, Piazzi made his suspicions clear: this could be the missing planet everyone was looking for. On hearing the news in late March, Bode wasted no time in announcing the discovery of a new planet, which he named Juno. Other astronomers preferred the name Hera, but Piazzi, still the only person who had actually seen the object, had opted for Ceres, after the Roman goddess of agriculture. By June, Ceres's orbit had taken it into the glare of the Sun. Piazzi had been sick in the interim and so had not had the chance to map anything but the simplest orbital arc. He calculated that his discovery would be visible again in the fall. But, try as they might, neither Piazzi nor anyone else could find Ceres. Piazzi's telescope, the Palermo Circle, was built by Jesse Ramsden. Its precision mounting allowed it to measure stellar positions with an accuracy of a few seconds of an arc. Mathematical hunch. Von Zach decided to follow a hunch, and sent the details of Ceres's orbit to the mathematician Carl Friedrich Gauss. In less than 6 weeks, Gauss calculated all the places Ceres was likely to be. It took von Zach most of December to search through Gauss's predictions, but on the evening of New Year's Eve 1801, almost exactly a year to the day after it was first seen, he found Ceres once again. The orbital distance of Ceres was 27.7 Bode units, a remarkably close fit to the predicted location. However, the orbital data showed that this new member of the solar system was far smaller than the known planets. William Herschel's early estimate put Ceres at just 160 miles across. A few years later, Schroeder proposed a diameter of 1,624 miles. The actual figure is 588 miles, which means it would be a comfortable fit over the Iberian Peninsula or Texas. The Celestial Police kept up the search and, in March 1802, Olbers discovered a second body like Ceres located at the same distance from the Sun, calling it Pallas. In 1804, Carl Harding found a third, named Juno, while it was Olbers again who spotted the fourth, Vesta, in 1807. All these bodies were later shown to be smaller than Ceres. Vesta and Pallas were slightly more than 300 miles wide and Juno was half that size. The evening of the third, my suspicion was converted into certainty, being assured it was not a fixed star. I waited till the evening of the fourth, when I had the satisfaction to see it had moved at the same rate as on the preceding days. Giuseppe Piazzi. Asteroid Belt. The Celestial Police called their discoveries minor planets, but William Herschel chose another name, asteroid, which means star-like. Herschel reasoned that, unlike true planets, these small objects had no discernible features, or at least none that could be made out with the telescopes of the day, so would be indistinguishable from starlight were it not for the fact that they moved. Perhaps still smarting from his failure to name the planet he had found 20 years earlier, Herschel qualified his suggestion by reserving for himself the liberty of changing that name, if another, more expressive of their nature, should occur. Nothing more expressive did occur, and after the Celestial Police was disbanded in 1815, a steady trickle of asteroid discoveries continued. By 1868, their number stood at 100, by 1985, it was 3,000. The advent of digital photography and image analysis has now boosted the number of recorded asteroids to more than 50,000, spread around the 28 Bode unit gap. Olbers and Herschel had discussed the possibility that the asteroids were the remains of a planet that once orbited in the gap before being smashed by an astronomical cataclysm. Today, it is thought that the gravitational disruption of nearby Jupiter prevented the asteroids from accreting into a planet in the first place, as similar disks had done elsewhere in the primordial solar system. Under constant influence from the cumulative gravity of other asteroids, about 80% of known asteroids have unstable orbits. The 13,000 or so bodies that come particularly close to Earth, the near-Earth asteroids, are monitored in the hope of predicting and preventing devastating future impacts. They resemble small stars so much as hardly to be distinguished from them. From this, their asteroidal appearance, if I take my name, and call them asteroids. William Herschel. The asteroid Vesta was visited by the Dawn spacecraft from 2011-12. Its orbit lies within that of Ceres, and it is the brightest asteroid as seen from Earth. Trojans. There are also asteroids known as Trojans, which travel in the same orbits as planets, gathering far from their host in gravitationally stable libration points. Most of these are in the Jupiter system, where they form two clusters, the Trojan camp and Greek camp. Mars and Neptune have Trojans, and the first Earth Trojan was discovered in 2011. In 2006, the International Astronomical Union gave Ceres the status of dwarf planet, the only one in the asteroid belt. At the same time, Pluto was reclassified as a dwarf planet. The orbits of neither Neptune nor Pluto match the predictions of Bode's law. Despite the fact that it was instrumental in the discovery of Ceres, Bode's law is now viewed as a mathematical coincidence, and not a key to unlocking the formation of the solar system. Giuseppe Piazzi. As was common for younger sons in wealthy Italian families, Giuseppe Piazzi's career began in the Catholic Church. By his mid-20s, it was obvious that his abilities lay in academia. In 1781, he was appointed math professor at a newly founded academy in Palermo, Sicily, but soon switched to astronomy. His first task in this role was to build a new observatory, which he equipped with the Palermo Circle, a telescope built in London with a 5-feet-wide altitude scale. It was the most accurate telescope in the world at the time. Piazzi was famed for his diligence, and would take measurements on at least 4 consecutive nights to average out errors. In 1806, he recorded the large proper motion of the star 61 Cygni. This prompted several astronomers to use the parallax of that star to measure the distance between stars. Key works: 1803 Praecipuarum Stellarum Inerrantium. 1806 Royal Observatory of Palermo. See also, elliptical orbits observing Uranus asteroids and meteorites. In context. Key astronomer John Herschel. Before 1784 Charles Messier publishes a list of 80 known nebulae. After 1887 the Cartes du Ciel, an ambitious project to survey the entire sky photographically, is initiated by the director of the Paris Observatory, Amédée Mouchet. 1918 the Henry Draper Catalogue, covering most of the sky, is published by Harvard College Observatory. 1948-58 the Palomar Observatory in California completes its major sky survey, which includes data from nearly 2,000 photographic plates. 1989-93 the Hipparcos satellite gathers data that allow more than 2.5 million stars to be catalogued. Between 1786 and 1802, William Herschel published catalogues listing more than 1,000 new objects in the night sky. Following his death in 1822, William's son John continued his work, but expanded its scope and ambition to carry out a complete survey of the night sky. William's observations had all been made from southern England, and so were limited to objects down to around 33 degrees below the celestial equator. To survey the rest of the sky, his son's observations would have to be made from somewhere in the southern hemisphere. Herschel settled on South Africa, then a part of the British Empire. He moved there in 1833, taking with him his wife and young family, an assistant, and his father's 20-feet focal-length telescope. This was the same instrument that had been used to survey the northern skies, and Herschel chose it to ensure that the new information gathered from the southern hemisphere was comparable to that already produced. The family set themselves up in a house near the base of Table Mountain, far enough away to avoid the clouds that often gathered on its summit, and Herschel spent the next 4 years completing his survey. The Milky Way's core is clearest from the southern hemisphere. The dark regions are where starlight is blocked by interstellar dust. The southern skies. The Magellanic Clouds are two dwarf galaxies close to the Milky Way, and are only visible from the southern hemisphere. They can be seen by the naked eye, but Herschel's telescopic surveys provided the first detailed observations available to astronomers. He compiled a list of more than 1,000 stars, star clusters, and nebulae within these galaxies. Herschel also made careful observations of the distributions of stars within the Milky Way. Due to the orientation of the solar system within the Milky Way, the brightest section of it, which is now known to be the core of the galaxy, is only visible low on the horizon from the northern hemisphere during the summer when nights are short. From the southern hemisphere, the brighter core is visible higher in the sky and during the darker months of the year, allowing easier and more detailed observations. The end result of Herschel's labors, the General Catalogue of Nebulae and Clusters of Stars, listed more than 5,000 objects in total. These included all the objects observed by John and his father, and also many discovered by others such as Charles Messier, since it was intended to be a complete catalogue of the stars. The stars are the landmarks of the universe. John Herschel. John Herschel. John Herschel left Cambridge University in 1816, already a renowned mathematician. He worked with his father, William, and continued his work after William's death in 1822. Herschel became one of the founders of the Royal Astronomical Society and served as president for 3 separate terms. He married in 1826 and fathered 12 children. Herschel had numerous interests in addition to astronomy. While in South Africa, Herschel and his wife produced a portfolio of botanical illustrations. He also made important contributions to photography, experimenting with color reproduction, and published papers on meteorology, telescopy, and other subjects. Key works. 1831 A Preliminary Discourse on the Study of Natural Philosophy. 1847 Results of Astronomical Observations made at the Cape of Good Hope. 1864 General Catalogue of Nebulae and Clusters of Stars. 1874 General Catalogue of 10,300 Multiple and Double Stars. See also, Messier Objects, the Milky Way, examining nebulae. In context. Key astronomer. Friedrich Bessel. Before 220 BCE Aristarchus suggests that the stars are very far away since no parallax can be seen. 1600 Tycho Brahe rejects the Copernican sun-centered system partly because he cannot detect stellar parallax. After 1912 Henrietta Swan Leavitt discovers a link between the period of a type of variable star and its brightness, allowing these stars to be used as standard candles for figuring out distances. 1929 Edwin Hubble discovers the link between the redshift of a galaxy's light and its distance from Earth. 1938 Friedrich Georg Wilhelm Struve measures the parallax of Vega, and Thomas Henderson measures the parallax of Alpha Centauri. Parallax is the apparent movement of a nearby object against distant objects due to the changing position of the observer. According to this phenomenon, nearby stars should appear to change position against the background of more distant stars as Earth moves around its orbit. The idea that it might be possible to measure the distance to nearby stars using parallax dates back to ancient Greece. However, it was not achieved until the 19th century, due to the distances involved being far greater than anyone supposed. Much of German astronomer Friedrich Bessel's career had been dedicated to the accurate determination of the positions of stars and finding their proper motion. By the 1830s, with improvements in the power of telescopes, there was a race to carry out the first accurate measurement of stellar parallax. In 1838, Bessel measured parallax with an angle of 0.314 arc-seconds for the star 61 Cygni, which indicated that it was 10.3 light-years away. The current estimate is 11.4 light-years, giving Bessel's measurement an error of just under 10%. Due to the effects of parallax, a nearby star's apparent position against distant background stars moves from B in June to A in December. See also, the Tychonic model measuring the universe beyond the Milky Way. In context. Key astronomer. Samuel Heinrich Schwab. Before 800 BCE Chinese and Korean astrologers record sunspots to help foretell events. 1128 English chronicler John of Worcester draws sunspots. 1801 William Herschel links sunspot numbers and the price of wheat, due to the effect of sunspots on Earth's climate. After 1845 French physicists Hippolyte Fizeau and Léon Foucault photograph sunspots. 1852 Irish astronomer Edward Sabine demonstrates that the number of magnetic storms on Earth correlates with the number of sunspots. 1908 U.S. astronomer George Ellery Hale discovers that sunspots are caused by magnetic fields. Sunspots are cooler areas on the sun's surface caused by changes in its magnetic field. The first written observations of sunspots date from about 800 BCE, in China, but it was not until 1801 that the British astronomer William Herschel made the connection between sunspots and changes in Earth's climate. Samuel Schwab, a German astronomer, started observing sunspots in 1826. He was looking for a new planet thought to orbit closer to the Sun than Mercury, provisionally named Vulcan. It would have been very difficult to observe such a planet directly, but Schwab thought he might see it as a dark spot moving in front of the Sun. He did not find Vulcan, but he did discover that the number of sunspots varied over 11-year cycles. Swiss astronomer Rudolf Wolff studied Schwab's and other observations, including some from as far back as Galileo, and numbered the cycles starting at 1 for the 1755-66 cycle. Eventually, he saw that there are long periods in each cycle when the number of sunspots is low. Herschel had not noticed the pattern because he was observing during what is now called the Dalton minimum, when overall numbers of sunspots were low. Sunspots can last from a few days to several months. The largest can be the size of Jupiter. See also, observing Uranus, the properties of sunspots. Carrington. In context. Key astronomer Lord Rosse. Before 1784 Charles Messier publishes a catalogue of the visible nebulae. 1785 William Herschel publishes catalogues of nebulae and speculates that many are similar in shape and size to the Milky Way. 1833 John Herschel expands his father's catalogues by surveying objects from the southern hemisphere. 1864 William Huggins discovers that some nebulae are clouds of luminous gas, not aggregations of stars. After 1917 Vesto Slipher concludes that spiral galaxies are island universes and that the Milky Way is one such galaxy seen by us from within. In the 1840s, a British aristocrat named William Parsons, Lord Rosse, decided to commit some of his considerable wealth to building the world's largest reflecting telescope. Rosse was curious to re-examine some of the nebulae listed by John Herschel in the early 19th century, in particular those nebulae that did not appear to be clusters of stars. To re-observe these nebulae, Rosse needed to build a larger and better telescope than that used by Herschel. He experimented for many years with methods for casting a 36-inch mirror. Mirrors at the time were made from a metal called speculum, an alloy of copper and tin, a brittle material that was prone to cracking as it cooled. Despite this difficulty, by 1845 Rosse had succeeded in casting a mirror that was 72 in diameter. He mounted it in his telescope at Bear Castle, near Parsonstown in Ireland, where it became known as the Leviathan of Parsonstown. This telescope remained the world's largest reflecting type until the 100 inches reflector was built at Mount Wilson in California in 1917. Central Ireland proved a far from ideal place to build a telescope, as overcast or windy conditions often prevented viewing. The telescope itself had limited mobility, meaning that only a small area of the sky could be examined. Nonetheless, when the weather was clear, Rosse was able to use the huge instrument to observe and record the spiral nature of some nebulae, now called spiral galaxies, for the first time. The first of these spirals that Rosse identified was M51, later known as the Whirlpool Galaxy. Today, about 3/4 of all the galaxies that have been observed are spiral galaxies. However, these are thought ultimately to transform into elliptical galaxies. Formed of older stars, elliptical galaxies are dimmer and much harder to spot, but astronomers believe that they are probably the most common galaxy type in the universe. The nebular hypothesis. In the mid-19th century, astronomers debated whether nebulae consisted of gas or stars. In 1846, Ross found numerous stars in the Orion Nebula, and so for a time, the idea of gaseous nebulae was rejected. However, although the stars were real, their presence did not mean that there was no gas. The gaseous nature of some nebulae was not demonstrated until spectroscopic analysis was used by William Huggins in 1864. The light by which we recognize the nebulae now must be merely that which left their surfaces a vast number of years ago. Phantoms of processes completed long in the past. Edgar Allan Poe. The Leviathan telescope at Parsonstown held a mirror weighing 3.3 tons, inside a 54 feet long tube. The whole structure weighed about 13 tons. Lord Rosse. William Parsons was born in Yorkshire in 1800 and became 3rd Earl of Rosse on the death of his father in 1841. He was educated at Trinity College, Dublin, and at Oxford University, where he was awarded a first-class degree in mathematics. He married in 1836, but only 4 of his 13 children survived to adulthood. Lord Rosse's estates were in Ireland, and this is where he built his telescopes. In 1845, after he made public his findings on nebulae, Rosse was criticized by John Herschel, who was convinced that nebulae were gaseous in nature. Both men accused each other of using flawed instruments. Ultimately, however, neither succeeded in demonstrating sufficient scientific evidence to resolve conclusively the question of whether nebulae were composed of gas or stars. Key works: 1844 on the construction of large reflecting telescopes, 1844 observations on some of the nebulae, 1850 observations on the nebulae. See also, Messier objects, the Milky Way, the Southern Hemisphere, properties of nebulae, spiral galaxies. In context. Key astronomer: Urbain Le Verrier. Before March 1781, William Herschel discovers Uranus. August 1781, Finnish Swedish astronomer Anders Lexell finds irregularities in Uranus's orbit and suggests that they are due to other, undiscovered planets. 1799, 1825, Pierre-Simon Laplace explains perturbations mathematically. 1821, French astronomer Alexis Bavard publishes predictions of future positions of Uranus. Subsequent observations deviate from his predictions. After 1846, Briton William Lassell discovers Triton, Neptune's largest moon, only 17 days after the discovery of the planet. 1915, Albert Einstein explains perturbations in the orbit of Mercury using relativity. In the months following William Herschel's discovery of Uranus in 1781, astronomers found irregularities, or perturbations, in its orbit. Most perturbations in orbits are caused by the gravitational effects of other large bodies, but with Uranus there were no known planets that could cause the observed motion. This led some astronomers to suggest that there must be a planet orbiting beyond Uranus. Calculations of Uranus's predicted orbit took into account the gravitational effects of the Sun, Jupiter, and Saturn. However, the observed orbit deviated from the calculations in a way that suggested the pull of another massive body farther out from the Sun. Searching for the invisible. Frenchman Urbain Le Verrier tackled the problem of the perturbations of Uranus by assuming the location of an undiscovered planet and using Newton's law of gravity to work out what its effect might be on Uranus. This prediction was compared to observations of Uranus, and the position was revised according to the planet's movements. After many repetitions of this process, Le Verrier established the likely position of an unknown planet. He presented his ideas before the Académie des Sciences in 1846, and he also sent his predictions to Johann Galle at the Berlin Observatory. Galle received Le Verrier's letter on the morning of September 23, 1846, and obtained permission to look for the planet. Working with his assistant Heinrich Darst, he located an unknown object within 1 degree of the predicted position that same night. Observations on subsequent nights showed that the object was moving against the background of stars and was, indeed, a planet, one that would later be named Neptune at Le Verrier's suggestion. Galle later gave the credit for the discovery to Le Verrier. Independent discovery. At the same time as Le Verrier was calculating the position of the unknown planet, British astronomer John Couch-Adams was also looking at the cause of the perturbations in the orbit of Uranus. He arrived at a similar conclusion to Le Verrier, completely independently, but his results were not published until after Gall had observed the new planet. There was some controversy over who should have the credit for the discovery, but Adams always acknowledged that Leverrier had the better claim. Gall was not the first person to observe Neptune. Once the orbit of Neptune had been worked out, it was possible to go through old records and find that others had already observed it without realizing it was a planet, including both Galileo and John Herschel. Later, Leverrier used a similar technique to analyze the orbit of Mercury and found that perturbations in its orbit could not be explained by Newtonian mechanics. He suggested that this might be due to the influence of another planet even closer to the Sun, provisionally named Vulcan. This speculation ended when Einstein explained the perturbations using his general theory of relativity. Urbain Leverrier. Urbain Leverrier studied at the École Polytechnique, near Paris. After graduating, his initial interests were in chemistry, before he switched to astronomy. His astronomical work was focused on celestial mechanics, the description of the movements of the bodies in the solar system using mathematics. Leverrier obtained a position at the Paris Observatory and spent most of his life there, acting as director from 1854. However, his management style was not popular and he was replaced in 1870. He took up the position again in 1873 after his successor drowned, and held it until his own death in 1877. Leverrier spent his early career building on Pierre-Simon Laplace's work on the stability of the solar system. He later went on to study periodic comets before turning his attention to the puzzle of Uranus's orbit. Key work: 1846 Recherches sur les mouvements de la planète Herschel, research on the movements of the planet Herschel. See also, the Milky Way gravitational disturbances, the theory of relativity. Introduction. In the early 19th century, astronomy was mainly concerned with cataloging the positions of stars and planets, and understanding and predicting the movements of the planets. New comets continued to be discovered, and there was a growing awareness of assorted distant phenomena, such as variable stars, binary stars, and nebulous objects. However, there seemed little scope for learning more about the nature of these remote objects, their chemical composition or temperature, for example. The key that unlocked these mysteries was the analysis of light using spectroscopy. Decoding starlight. A glowing object gives out light over a range of wavelengths, which we perceive as a rainbow of colors from the longest wavelength to the shortest. When a spectrum is examined in close detail, a multitude of fine variations can emerge. A typical star spectrum appears crossed by numerous dark lines, some fine and faint, some broad and black. Such lines in the Sun's spectrum had been noted as early as 1802, but the first physicists to examine the physics behind particular kinds of spectra were Gustav Kirchhoff and Robert Bunsen. Importantly, in about 1860, Kirchhoff showed that different patterns of dark lines are the spectral fingerprints of different chemical elements. Here was a way to investigate the composition of the Sun and stars. It even led to the discovery of the previously unknown element, helium. This new branch of astronomy was enthusiastically taken up by the British astronomer William Huggins and his wife, Margaret, who also pioneered photography as a way of recording observations. They did not restrict themselves to stars, but studied the spectra of nebulae as well. By the end of the 19th century, it seemed that, in order to fully understand the nature of stars, it was necessary to systematically record their spectra and classify them into different types. Light is to us the sole evidence of the existence of these distant worlds. James Clerk Maxwell. Star classification. This immense task was undertaken at Harvard College Observatory, where the director Edward Pickering employed a large team of women to carry out the exacting work. Here, Annie Jump Cannon devised the stellar classification system still used today, based on a temperature sequence. Cannon personally classified some 500,000 stellar spectra. The star catalog included not only their position but also precise information about their magnitude and spectrum. This information quickly paid dividends as astronomers analyzed the new data. Cannon's colleague at Harvard, Antonia Mori, realized that the simple temperature sequence did not take account of subtle variations within each star type. Ejner Hertzsprung and Henry Norris Russell independently followed this up, leading to the discovery that stars of the same color could be giants or dwarfs, and the identification of the first known white dwarf star. The physics of the stars. In an interval of some 50 years, cutting-edge astronomy had changed its focus. By the early 20th century, physics, the study of matter, forces, and energy, and how they are related, could be applied to the sun and stars, and would strongly influence the future direction of astronomy. Significant developments in basic physics impacted on astronomy. For example, Briton James Clerk Maxwell published his theory of electromagnetism in 1873, describing electromagnetic radiation such as light in terms of its wave-like properties. X-rays were discovered in 1895 and radioactivity in 1896. In 1900, German physicist Max Planck prepared the ground for quantum physics with a leap of inspiration, postulating that electromagnetic energy comes in packets of a particular size, called quanta. These discoveries would lead to new ways of looking at the skies, and shed new light on the processes taking place within stars. Physics and astronomy would be inseparable from this point on. In context. Key astronomer. Gustav Kirchhoff before 1802. After creating an image of the sun's spectrum by passing sunlight through a narrow slit and prism, English chemist William Hyde Wollaston notices 7 dark lines in the spectrum. 1814. Joseph von Fraunhofer, the German inventor of the spectroscope, discovers 574 of the same dark lines in the sun's spectrum. He maps these in detail. After 1912, Danish physicist Niels Bohr introduces a model of the atom in which movements of electrons switching between different energy levels cause radiation to be emitted or absorbed at particular wavelengths. In 1814, a German maker of optical instruments named Joseph von Fraunhofer invented the spectroscope. This allowed the spectrum of the sun, or any other star, to be displayed and measured with high precision. Fraunhofer noticed that there were more than 500 dark lines crossing the sun's spectrum, each located at a precise wavelength. These came to be known as Fraunhofer lines. By the 1850s, German scientists Gustav Kirchhoff and Robert Bunsen had discovered that, if different chemical elements are heated in a flame, they emit light at one or more wavelengths that are characteristic for that element, acting like a fingerprint to indicate its presence. Kirchhoff noticed that the wavelengths of light given off by some elements corresponded to the wavelengths of some Fraunhofer lines. In particular, sodium's emissions at wavelengths of 589.0 and 589.6 nanometers exactly matched 2 Fraunhofer lines. Kirchhoff suggested that a hot, dense gas, such as the sun, will emit light at all wavelengths and thus produce a continuous spectrum. However, if the light passes through a cooler, lower-density gas, such as the sun's atmosphere, some of that light might be absorbed by an element, at the same wavelengths at which the element emits light when heated. The absorption of the light causes gaps in the spectrum, which are now known as absorption lines. The path is opened for the determination of the chemical composition of the sun and the fixed stars. Robert Bunsen. See also, Analyzing starlight, the characteristics of stars, refining star classification, stellar composition. In context. Key astronomer Angelo Secchi. Before 1802, William Hyde Wollaston notices that there are dark gaps in the sun's spectrum. 1814, German lensmaker Joseph von Fraunhofer measures the wavelengths of these dark lines. 1860, Gustav Kirchhoff and Robert Bunsen use a gas burner to make systematic recordings of the wavelengths produced by burning elements. After 1868, English scientist Norman Lockyer identifies a new element, helium, from emission lines in the sun's light. 1901, the Harvard system for the classification of stellar spectra, devised by Williamina Fleming and Annie Jump Cannon, supersedes Secchi's system. Angelo Secchi was one of the pioneers of astrophysics, an arm of science that focuses on the properties of a star, rather than merely its position in the sky. He was the first to group stars according to their spectra, or the particular colors of light they emit. A Jesuit priest as well as a noted physicist, Secchi founded a new observatory at the Order's Collegio Romano in Rome. There he became a pioneer of the technique of spectroscopy, a new way to measure and analyze starlight. Gustav Kirchhoff had shown that gaps in a stellar spectrum were caused by the presence of specific elements. Armed with this knowledge, Secchi began to class stars according to their spectra. At first he used three classes. Class 1 were white or blue stars that showed large amounts of hydrogen in their spectra, Class 2 were yellow stars, with metallic spectral lines, and Class 3 were orange, with a complex array of elements present. In 1868, Secchi added Class 4 for redder stars with carbon present, and finally in 1877 came Class V for stars that showed emission lines. Secchi's stellar classes were later amended by other scientists, and in 1880 became the foundation of the Harvard system, which is used to classify stars to this day. Spectroscopy uses a prism to refract the light from a star, splitting the light to allow its constituent wavelengths to be measured with a high degree of accuracy. See also, the Sun's spectrum, the Sun's emissions, the star catalog, the characteristics of stars. In context. Key astronomer. William Huggins. Before 1786 William Herschel publishes a list of nebulae. 1850s Gustav Kirchhoff and Robert Bunsen realized that hot gases produce bright emission lines in their spectra of light, whereas cool gases absorb the same wavelength, producing dark lines in spectra. After 1892 Margaret Huggins is made an honorary Fellow of the Royal Astronomical Society. 1913 Dane Niels Bohr depicts atoms as containing a central nucleus surrounded by electrons. Spectral lines are produced when the electron moves between energy levels. 1927 American Ira Bowen realizes that the two green lines caused by a nebulum are produced by oxygen atoms that have lost two electrons. In the 1860s, a pioneering British astronomer named William Huggins made key discoveries by studying the composition of stars and nebulae using a spectroscope. This instrument, a glass prism attached to a telescope, splits white light into its constituent light wavelengths, producing a spectrum of color. Gustav Kirchhoff and Robert Bunsen had already noted the chemical composition of the Sun by studying the dark absorption lines that occur in its spectrum. These lines are caused by the atoms of different chemical elements absorbing radiation at certain precise wavelengths. Huggins, encouraged by his astronomer wife, Margaret, turned his attention deeper into space, toward nebulae, the fuzzy patches of light that had long mystified astronomers. He used spectroscopy to divide these patches into two distinct types. The spectra of nebulae. Huggins observed that nebulae, such as the Andromeda Nebula, had a spectrum of light similar to that of the Sun and other stars, a broad band of color with dark absorption lines. The reason for this was that such nebulae are indeed composed of stars, and are galaxies in their own right. The second type of nebula he observed was entirely different. Its light spectrum was made of single wavelength emission lines, energy was being emitted as one color, there were no absorption lines. Huggins realized that these second kind of nebula were huge clouds of hot, low-density gas. Some of this gas could be in the process of forming new stars, other gas clouds, like the planetary nebulae, could have been ejected from evolving stars. Huggins' 1864 observations of the Cat's Eye Planetary Nebula in the constellation Draco revealed a spectrum with a single absorption line, produced by hot hydrogen gas. However, the nebula also emitted energy in two strong green lines, which did not correspond to any known chemical element. Some astronomers suggested that they were produced by a new element, dubbed nebulum. Huggins concluded from his spectroscopic observations that all of the heavenly bodies he had studied were made of exactly the same elements as Earth. However, the mystery of nebulum was not solved until after his death. In 1927, it was found to be simply doubly ionized oxygen atoms that have lost electrons and have a double positive charge. Huggins was the first to analyze the spectrum of a planetary nebula, confirming that it was gaseous and not composed of stars. William Huggins. After selling the family drapery business when he was 30, William Huggins ran a private observatory in Tulse Hill in South London. He used his new wealth to buy a powerful 8 inches refracting telescope. In 1875, age 51, Huggins married 27-year-old Irish astronomy enthusiast Margaret Lindsay, who encouraged him to adopt photography to record his spectra and was an active partner in his later research, co-authoring many papers. Huggins was a pioneer in the use of photography to record astronomical objects. He also developed a technique to study the radial velocity of stars using the Doppler shift of their spectral lines. As a pioneer astronomical spectroscopist, Huggins was elected to serve as president of the Royal Society from 1900 to 1905. He died at his home in Tulse Hill in 1910, age 86. Key works: 1870 Spectrum analysis in its application to the heavenly bodies. 1909 Scientific papers. See also, Observing Uranus Messier objects, the Sun's spectrum. In context. Key astronomers Jules Janssen, Joseph and Norman Lockyer. Before 1863 Gustav Kirchhoff developed spectroscopy, showing how light can be used to identify hot substances. 1864 William and Margaret Huggins find that the spectra of nebulae contain different emission lines, showing that they are largely clouds of gas. After 1920 Arthur Eddington states that stars are fueled by the fusion of hydrogen into helium. 1925 Cecilia Payne-Gaposchkin shows that stars are largely made from the elements hydrogen and helium. 1946 U.S. cosmologist Ralph Alpher calculates that most of the universe's helium was formed in the first few minutes after the Big Bang. In August 1868, the French astronomer Pierre-Jules César Janssen traveled to India to observe a solar eclipse. The eclipse covered the sun's bright disk, leaving only a narrow ring of light. This was the chromosphere, the middle of three layers in the sun's atmosphere, which was normally hidden by the glare. Janssen found that the spectrum of the chromosphere's light contained numerous bright emission lines. Using discoveries made by Gustav Kirchhoff, Janssen was able to confirm that the chromosphere was a layer of gas. He also noticed a previously unseen yellow emission line in the sun's spectrum. He assumed this unknown light was produced by sodium, helping to give the sun its yellow hue. In October that year, English astronomer Joseph Norman Lockyer developed a spectroscope for observing the chromosphere directly. He also detected its curious light and also assumed it was produced by sodium, but after consulting the chemist Edward Frankland, he changed his mind. The light was not from sodium but from a hitherto unknown element, which he named helium, after Helios, the Greek word for the sun. For some years, it was thought that helium only existed on the sun, but in 1895, Scottish chemist William Ramsay succeeded in isolating a sample from a radioactive uranium mineral. A total eclipse of the sun reveals the chromosphere. This image of an eclipse was captured in 1919 by British astronomer Arthur Eddington. See also, the sun's spectrum, nuclear fusion within stars, the primeval atom. In context. Key astronomer Giovanni Schiaparelli. Before 1858 Angelo Secchi first uses the word canali in connection with Mars. After 1897 Italian astronomer Vincenzo Cerulli theorizes that the Martian canals are just an optical illusion. 1906 A book by American astronomer Percival Lowell, Mars and Its Canals, promotes the idea that there may be artificial canals on Mars, built by intelligent beings. 1909 Photographs of Mars taken at the New Bail-Law Dome at the Pic du Midi Observatory in France discredit the Martian canals theory. 1960s NASA's Mariner flyby missions fail to capture any images of the canals or find any evidence of them. By the mid-19th century, scientists were increasingly speculating about the possibility of life on Mars, which had been found to have certain similarities to Earth, including ice caps, a similar length of day, and an axial tilt that meant it experienced seasons. However, it had also been found that it did not rain on Mars. Between 1877 and 1890, Italian astronomer Giovanni Schiaparelli carried out a series of detailed observations of Mars to produce a map of the planet's surface. Schiaparelli described various dark areas as seas and lighter areas as continents. He also portrayed what seemed to him to be a network of long, dark, straight lines, or streaks, crisscrossing Mars's equatorial regions. In his book Life on Mars, Schiaparelli suggested that, in the absence of rain, these channels might be the mechanism by which water was transported across the dry surface of the planet to allow life to exist there. In the following years, many eminent scientists, including American astronomer Percival Lowell, speculated that these dark lines were irrigation canals constructed by intelligent beings on Mars. However, others could not see the channels at all when they looked for them, and by 1909, observations with telescopes of higher resolution had confirmed that the Martian canals did not exist. Schiaparelli's 1888 Atlas of Mars shows land, seas, and a network of straight channels. Here, the South Pole is shown at the top. See also, observing Saturn's rings, analyzing starlight life on other planets. In context. Key astronomer David Gill. Before 1840, the first clear photograph of the Moon is taken by American John Draper, using a 20-minute exposure. 1880, John Draper's son Henry takes a 51-minute exposure of the Orion Nebula. He also takes the first wide-angle photograph of the tail of a comet. After 1930, U.S. astronomer Clyde Tombaugh discovers Pluto by spotting a moving object on photographic plates. 1970s charge-coupled devices replace photographic plates and film with digital photographs. 1998, the Sloan Digital Sky Survey begins to make a 3D map of galaxies. Isaac Newton's theory of gravitation, like many advances of the scientific revolution, was based on a belief that the universe worked like clockwork. In the 1880s, David Gill, a master clockmaker from Aberdeen, Scotland, applied his precision clockmaking machinery to astronomical telescopes and, ironically enough, offered a way of showing that the stars were not all moving in clock-like unison. Gill was a pioneer in the field of astrophotography. In the mid-1860s, then still an amateur astronomer working in his father's backyard, he built a tracking mount for his 12 inches reflecting telescope, and used it to photograph the Moon with a clarity that had never been seen before. The photographs earned Gill a fellowship in the Royal Astronomical Society, and, by 1872, his first job as a professional astronomer at the Denect Observatory in Aberdeen. Gill applied clockwork tracking mechanisms to telescope mounts so that the telescope could move in near-perfect harmony with the rotation of Earth. This allowed the instrument to remain fixed and focused on a single patch of sky. Gill was not the first to attempt to photograph the heavens with telescopes, but imaging faint celestial light required exposures of several minutes at least, and poor tracking meant that early star photographs were mostly incomprehensible blurs. Southern sky. In 1879, Gill became the chief astronomer at the Cape Observatory in South Africa. By now, he was using the latest dryplate system, which he employed to capture the Great Comet that appeared over the southern hemisphere in 1882. Working in partnership with the Dutch astronomer Jacobus Kapteyn, Gill spent the best part of the next 2 decades creating a photographic record of the southern sky. The result was the Cape Photographic Durchmusterung, showing the position and magnitude of nearly 500,000 stars. Gill also became a key figure in the Carte du Ciel project, a global collaboration of observatories begun in 1887 with the goal of making a definitive photographic map of the stars. This ambitious, expensive, and decades-long project involved teams of human computers who would measure the plates by hand. It was, however, superseded by new methods and technologies before it was finished. The accurate maps produced by Gill's photographic techniques may seem fairly unremarkable today, but at the turn of the 20th century they were the first reliable means for showing the proper motion of nearby stars relative to more distant ones. This information was invaluable for measuring stellar distances on a large scale, and it began to reveal to astronomers the true scale of the galaxy and the universe beyond. Frank McLean, an astronomer friend of David Gill, donated the McLean telescope to the Cape Observatory in 1897. David Gill used it extensively. David Gill. The eldest son of a successful clockmaker, David Gill was destined to take over the family business. However, while at the University of Aberdeen, he became a student of the great physicist James Clerk Maxwell, whose lectures gave Gill a passion for astronomy. When offered a job as a professional astronomer in 1872, Gill sold the family business and began work at the Denect Observatory, Aberdeen. In addition to his pioneering work in astrophotography, Gill developed the use of the heliometer, a device for measuring stellar parallax. His measurements, used in conjunction with his star maps, did much to reveal the distances between stars. By the time he left the Cape Observatory in 1906, Gill was a renowned astronomer. In one of his final jobs, the government consulted him on the implementation of daylight saving hours. Key work: 1896, 1900 Cape Photographic Durchmusterung. See also, the Tychonic model mapping southern stars. Messier Object Space Telescopes, a digital view of the skies. Roberts Captain Barnard. In context. Key astronomer: Edward C. Pickering. Before 1863, Angelo Secchi developed spectral classification for stars. 1872, American amateur astronomer Henry Draper photographs the spectral lines of Vega. 1882, David Gill begins to survey the southern sky using photography. After 1901, Annie Jump Cannon, along with Pickering, creates the Harvard classification scheme, which forms the basis of stellar classification. 1912, Henrietta Swan Leavitt links the period of Cepheid variables to their distance. 1929, Edwin Hubble measures the distance to nearby galaxies using Cepheid variables. Edward C. Pickering, in his role as director of the Harvard College Observatory from 1877 to 1906, laid the foundations for precise stellar astronomy. His team carried out star surveys that broke new ground in understanding the scale of the universe. Pickering combined the latest techniques in astrophotography with spectroscopy and photometry to create a catalog that listed a star's location, magnitude, and spectral type. He did this with the help of the Harvard computers, a team of mathematically minded women upon whom Pickering relied to process the huge amounts of data required to create the catalog. More than 80 computers, known in those less enlightened days as Pickering's harem, worked at the Harvard Observatory. The first of them was Williamina Fleming, who had been Pickering's maid. Upon taking over the observatory, Pickering fired his male assistant, deeming him inefficient, and hired Fleming in his place. Other notable names among the computers included Antonia Mori, Henrietta Swan Leavitt, and Annie Jump Cannon. A woman had no chance at anything in astronomy except at Harvard in the 1880s and 1890s. And even there, things were rough. William Wilson Morgan, U.S. astronomer. Color and brightness. Pickering's individual contributions to the star catalog were twofold. In 1882, he developed a method of photographing multiple star spectra simultaneously by transmitting the star's light through a large prism and onto photographic plates. In 1886, he designed a wedge photometer, a device for measuring the apparent magnitude of a star. Magnitudes had previously been recorded psychometrically, using the naked eye as a means of comparing one star's brightness with that of another. The wedge photometer was much more objective. The observer viewed a target star alongside one of several stars with an accepted brightness and then edged a wedge of calcite in front of the known source, diminishing its magnitude in increments until the two sources looked to have the same brightness. In 1886, Mary Draper, the widow of spectral photography pioneer Henry Draper, agreed to fund Pickering's work in her husband's name. In 1890, the first Draper catalog of stellar spectra was published. Pickering then opened an observatory in Arequipa, Peru, to survey the southern sky and produce the first all-sky photographic map. In combination with the work of the Harvard computers, Pickering's data was the basis for the Henry Draper catalog published in 1918, which contained spectral classifications for 225,300 stars across the entire sky. I do not know if God is a mathematician, but mathematics is the loom on which God weaves the universe. Edward C. Pickering. Many of the Harvard computers were trained in astronomy, but as women, they were excluded from academic positions. Their wages were similar to those of unskilled workers. Edward C. Pickering. Edward C. Pickering was the dominant figure of American astronomy at the turn of the 20th century. Many of the first steps in the development of today's astrophysics and cosmology were made by people he employed at the Harvard College Observatory. Known as a progressive for his attitudes to the education of women and their role in research, Pickering nonetheless asserted a rigid authority over his team. On more than one occasion, he forced out researchers with whom he did not agree, only for them later to be proved right. One example of this is Antonia Mori, whose work on stellar spectra Pickering dismissed. Pickering spent his whole career in academia, but was also an avid outdoorsman, and was a founding member of the Appalachian Mountain Club. The club became a leading voice in the movement to preserve wilderness areas. Key works: 1886 An Investigation in Stellar Photography, 1890 Draper Catalogue of Stellar Spectra, 1918 Henry Draper Catalogue. See also, the Sun's Spectrum, the characteristics of stars, analyzing absorption lines measuring the universe. In context. Key astronomer. Any jump cannon before 1860 Gustav Kirchhoff shows that spectroscopy can be used to identify elements in starlight. 1863 Angelo Secchi classifies stars using their spectra. 1868 Jules Janssen and Joseph Norman Lockyer discover helium in the solar spectrum. 1886 Edward Pickering begins compiling the Henry Draper Catalogue using a photometer. After 1910 The Hertzsprung-Russell diagram reveals the different sizes of stars. 1914 U.S. astronomer Walter Adams records a white dwarf. 1925 Cecilia Payne-Gaposchkin finds that stars are composed almost entirely of hydrogen and helium. American astronomer Annie Jump Cannon was the early 20th century's leading authority on the spectra of stars. When she died in 1941, Cannon was described as the world's most notable woman astronomer. Her great contribution was to create the basis of the system for classifying the spectra of stars that is still in use today. Cannon worked at the Harvard College Observatory as part of the team of Harvard Computers, a group of women employed by the director Edward C. Pickering to help compile a new stellar catalog. The college's catalog, begun in the 1880s with funding from the widow of astrophotographer Henry Draper, used new techniques to collect data on every star in the sky brighter than a certain magnitude, including obtaining the spectra of as many stars as possible. In the 1860s, Angelo Secchi had set out a provisional system for classifying stars according to their spectra. Pickering's team modified this system. By 1924, the catalog contained 225,000 stars. Each substance sends out its own vibrations of particular wavelengths, which may be likened to singing its own song. Annie Jump Cannon. Early approaches. Williamina Fleming, the first of Pickering's female computers, made the earliest attempt at a more detailed classification system by subdividing Secchi's classes into 13 groups, which she labeled with the letters A to N, then adding O, P, and Q. In the next phase of the work, fellow computer Antonia Mori, working with better data received from observatories around the world, noticed more variety in the detail. She devised a more complex system of 22 groups designated by Roman numerals, each divided into 3 subgroups. Pickering was concerned that applying such a detailed system would delay the task of compiling the catalog. However, Mori's approach to stellar classification proved a crucial step toward the creation of the Hertzsprung-Russell diagram in 1910, and consequent discoveries about stellar evolution. Cannon joined the Harvard College Observatory staff in 1896 and began working on the next part of the catalog, which was published in 1901. With Pickering's approval, to make classification clearer and easier, she reverted to Fleming's spectral classes designated by letters, but she changed the order. Mori had realized that stars of similar colors have the same characteristic absorption lines in the spectra. She had also deduced that a star's temperature is the main factor affecting the appearance of its spectrum and made her classes a temperature sequence from hotter to cooler. On this, Cannon followed Mori's lead. Some of Fleming's letters were dropped because they were unnecessary, so the final sequence became O, B, A, F, G, K, M, based on the presence and strength of certain spectral lines, especially those due to hydrogen and helium. Students of astronomy still learn it by remembering the mnemonic, "Oh be a fine girl, kiss me," attributed to Henry Norris Russell. The 7 main classes of star, categorized according to spectra and temperature, are, from left to right, O, B, A, F, G, K, and M, with O the hottest and M the coolest. Harvard system. Cannon's 1901 system laid the foundations for the Harvard spectral classification system. By 1912, she had extended it to introduce a range of more precise subclasses, adding 0 to 9 after the letter, with 0 the hottest in the class and 9 the coolest. A few new classes have been added since. The Harvard system essentially classifies stars by temperature and takes no account of the luminosity or size of the star. In 1943, however, luminosity was added as an additional dimension, creating the Yerkes classification system, otherwise called the MK